I'm Jerry Brinkley.
I'm Cannon Hughes.
And I'm Brennan Gallegos, and this is our group project over electron charge.
Relevant to problem. We chose our problem to be two small identical spheres, each with a mass of 0.05 kg, are suspended from insulating strings of length of 0.40 meters. The spheres are given equal charges of positive 5 times that by 10 to the negative 6 power Columbus, and repel each other until the strings make an angle of 10 degrees with the vertical. The question is to calculate the magnitude of the electrostatic force between the spheres. So the relationship that the electron charge shares with this problem is it uses the Coulomb's law. The force is equal to the constant of Q1 times by Q2 over R2 to find the repulsive force. Connection to earlier parts builds on previous topics like point charges, Coulomb's law, and vector decomposition of forces. Sequence this problem combines electric force concepts with mechanical equilibrium, giving a real-life application of electrostatics and physics. Benefits of the problem: understanding force between charges, applying geometry and trigonometry in physics, uh, scientific notation practice, transferable skills to problems with multiple charges or lab setups. Alternative choices considered. These are problems that we decided not to do. Calculate the electric force between 2 point charges separated by 0.10 meters. One with plus 3. That little weird U is microcoulombs. So plus 3 microcoulombs, and the other is negative 2 microcoulombs. Why we didn't choose this problem was because of it being simple. This is just a direct one-step Columbus law calculation. Question 2. Three equal charges, each with a positive 5 times by, I believe it's 10 to the negative 6 power at the corners of the equilibrium triangle. Uh, 0.20 meters, calculate the net electrostatic of the charges. Our group wanted a clear, stepwise process, introduces geometry and Coulomb's law, adding extra vector complexity. Involves vector addition of forces at equilibrium. Development of problem. We developed this problem that combined electrostatics with a realistic physical setup rather than using abstract point charges. We designed a scenario with charged spheres suspended on strings, allowing us to calculate force using Coulomb's law while considering geometry, the angle, and separation. Many of the textbook problems just ask for the force between the two charges at a fixed distance, while our problem requires calculating horizontal separation from the string length and angle, then applying Coulomb's law, which in our opinions adds a more meaningful multi-step element. The problem does avoid complex 3D vector addition, multiple charges, or motion over time.
Uniqueness of problem. The question is unique compared to other questions on the internet because our question uses spheres instead of point charges. The point charges have no physical size. Our question, however, uses real objects. Also implies center to center distance must be considered, as well as encourages thinking about real world charge distribution. Typical questions are asked are what is a force without specifying? Why our question is unique is because it specifically trains correct vector understanding of electric forces. And the visual for problem, this is a table right here. 1 times 10 to the negative 7 power. That'd be the first one. And then shows a table after that. But In this system of two charged spheres suspended by strings, several mathematical relationships describe how the spheres interact. The electric repulsive force follows a quadratic relationship with charge Fe times Q squared, meaning doubling the charge quadruples the force. The force also obeys an inverse square relationship with separation distance Fe times 1 r squared, decreasing rapidly as the spheres move farther apart.
You got the formulas in the step. For step one, it's N equals Q over E. And then step two, you substitute the values. And it's N equals 0.5 times 10 to the negative 6 power over 1.602 times 10 to the negative 9th power. Then for the third step, you divide the numbers, or you divide that same equation, and then you subtract the exponents, 10 to the negative 6 power and over 10 to the negative 19th value. And then you take, and that equals 10 to the 13th value. And then for your final answer, n equals 3.12 times 10 to the 13th power. And that's your correct answer for that. Uh, for this one, the electron is accelerated through a potential difference of 500 volts. Question: what is kinetic energy gained by the electron? For the solution, we were asked the kinetic energy gained by the electron accelerated through potential difference 500 volts. The energy gained by a charge Q moving through potential difference volts is K E equals Q times volts. Here would be Q equals E equals 1.602 times 10 to the 19th negative power, and 500 volts. Then substitute KE, and equals 1.602 times 10 to the negative 19th power times 500. And then you multiply that equation and get 801. And then you would take the KE 801 times 10 to the negative 19th power. And you get your other equation. And for your final answer, it'd be KE equals 801 times 10 to the negative 17th. The solution of the problem. For this problem, metal plate has a net charge of negative 3.204 times 10 to the negative 18th. And how many extra electrons are on the plate? The solution is the net charge on the plate is negative 3.204 times 10 to the 18th of a charge of an electron, and E equals 1.602 times 10 to the negative 19th. And the number of electrons is N equals Q over E. And you substitute the values, and you get the equation N equals 3.204 times 10 to the negative 18th power over 1.602 times 10 to the negative 19th power. And then you would divide them two and multiply it by N equals 2 times 10 would give you 20. Therefore, you have 20 extra left.